Okay, so first of all, I'm very pleased to be here, and thank you for inviting me to the Indonesia Battery Conference. I think nowadays it's quite clear Indonesia is in the center stage of the world because it is considered as the capital of nickel, which is a very important element for the battery industry. So my talk today will focus around the current situation for the battery research and also what I think in the next decade for the battery research. So I think let me put everyone on the same page first by saying that in the next 10 years, less than 10 years actually, we are hoping to electrify 1 billion cars for the world. And of course, everybody knows your smartphones and the tablets and computers are already powered by the lithium ion batteries. And all of these, we hope to provide the quality of life for about 8.5 billion people by 2030, and more than half of them are actually living in the population very dense countries. So it's very important when we think about the battery industry, we have to think about not only better energy density, power density, but also think about the recycling and sustainability issue of batteries. So just to give everyone a very quick overview of batteries. So battery has very rich history. Indeed, in 1800, Sir Alexandra Volta from Italy, the Volta pile, today I still use the Volta pile to demonstrate to the high school students how a battery works. And in the 1860s, you have the invention of the lead acid battery. And in the 1960s, you have Olshansky invented the nickel metal hydride batteries. And it's very important to realize that these battery chemistry today still with us. They did not replace any of the older application, but only unlock new applications. So by the time in the 1970s and 80s, Professor Stanley Whittingham and Professor Goodenough discovered the lithium intercalation chemistry, which lead to the commercialization of the first lithium-ion cells in 1992. We are around 30 years for lithium-ion batteries commercialization, but the research started more than 10 years before the commercialization. And even though in 2019, the Nobel Prize was awarded for intercalation chemistry for lithium ion batteries, for the young students who are in the audience today, one have to realize that we have many emerging markets where they are waiting for new battery chemistry to unlock the potentials. Things like Internet of Things, robots, flying drones, and ultimately we're hoping to use batteries to resolve the intermittency issues with the renewable sources like solar and wind. So the research activities will continue to push on because the history already told us whenever we have a new battery, more improved battery chemistry, we do not replace the old ones. We simply unlock new chemistries. Of course, today's electric vehicles mostly use the lithium-ion batteries, so it's very important for us to take a look what happened in the lithium-ion batteries for the last 30 years. In the battery electrochemistry, material science, physics, and engineering are very important. Actually, this comes from my class. The class I taught, I teach in UC San Diego, is to really have students learn about intercalation chemistry. And when you have a enclosed system like a battery, just look at your phone, the matters do not flow in and flow out. In fact, they are only shuffle between the two electrodes. You have negative electrodes, positive electrodes, and these positive electrodes is where a lot of the cobalt and nickel are being utilized. And the lithium have very different chemical potential when they shuffle between these two electrodes. So the thermodynamic Nernst equation is the best guiding equations to tell us why you have more than 4 volts in the lithium ion cells is because lithium, for example, has very different chemical potential in the transition metal oxides versus graphite, right? So this is one of the important take-home message. lithium ions actually is a big ion. It occupies large space. So if I do an X-ray photograph, it's like X-ray diffraction photographs of the battery, you will see this is how X-ray peak is going to move. It's going to move when you charge and discharge the battery. So you can see the peak moves, and sometimes one peak becomes two peak. That's a phase transition. And when you discharge the battery back, the process has to be completely reversible. So one don't realize, because your battery, your cell phone is typically enclosed in a hard casing, so you don't really visualize the volume change, but the X-ray tells you what your eyes cannot see. In fact, every time you discharge your batteries, the volume change for these intercalation materials will happen. The other important things happened in our field for the last 30 years is that almost all the known compounds in the database, if they have not been experimentally explored, they have been computationally evaluated if they are good battery materials. So typically we look for suitable voltage, and we look for capacity of the lithium intercalation capacity. So again, oxides is very attractive. So because there's several candidates of the oxides, they are in the right range, and they can provide a very, very high capacity. So when we think about the battery research in my group, we spend a lot of time to use advanced characterization techniques like X-ray, neutron, NMR-based technique to understand in every level of a battery, right? All the way from atom level to particle level to electrode level, where are the degradation mechanism happens, what kind of interface it forms. We have to do that because in every part of this scale bars, if something happens that caused inefficiency of the batteries, you can see that the battery with only 99% Coulombic efficiency will quickly degrade after 300 cycles. But for a good battery, you need to have very, very high Coulombic efficiencies, preferably with 3 nines. So this is imposed very significant challenges for scientists who work in the battery field. We have to find ways how all these characterization tools can help us to evaluate where is the degradation mechanism in the battery materials. So this is one of the examples we have shown that in the layered lithium transition metal oxide, what you see here, they are real images of the cathode materials that are made of lithium, nickel, manganese oxide. And you can actually see the transition metal like nickel and the manganese arranged beautifully when you make these crystals. However, after very high voltage exposure, this is cycled up to 4.8 volt, you can see the phase transformations, the changes in especially on the surface field layers of these oxides. So this was the first examples we have demonstrated that for the cathode materials, we have to find ways to protect the surface, especially if the cathode is being exposed to high voltage, because at the high voltage, we can have oxygen loss, and then also the transition metal, nickel and manganese will migrate to the lithium layer and causing serious impedance growth. So this is one of the early examples where we show that these atomic resolution imaging method can help the engineers and scientists to pinpoint where is the problem and how to resolve the problem. Right. So this is a famous Chinese saying, if you want to do a difficult job well, you must use the right tools. So in fact, we have developed many advanced characterization tools aimed at studying the material's bulk structure, interface, and then we have to actually manage the thermal, mechanical, electrical, and chemical reactions in a battery. So remember that the battery is a system. So for a system to work very well, every piece have to come together and function very well. So if you look at what happened this is almost 30 years, right? So this graph coming from Argonne National Lab is a roadmap that many of the people in our field utilize to think about the future for the battery research. If you think about the energy per weight and the energy per volume, here is where the Tesla cars or Nissan electric cars lies. And we have in the scientific laboratories many options to either give you higher volumetric energy density or higher gravimetric energy density. So all in all, even without changing the chemistry, just by engineering, the field has been able to triple the energy density in the last 30 years. In the 1991, when the first 18650 cell was made, it's only 1 amp hour with 3.6 volts, so it's about 3.6 watt hour, right? But today, it's easily you can go to 3.5 amp hour, right? So energy density for the batteries has improved dramatically. Perhaps the most striking improvement is the reduction in the cost. With the economy of scale and improvement in the manufacturing method, we have lowered the cost more than 10 times. And we can also now extend the cycle life to very, very long cycles, more than 1,000 cycles. And in the world right now, there's over 160 gigawatt hour worldwide production capacity. And we are confident in the next 10 years, it will grow at a 10 times speed. Because of that, I think everybody is asking, oh, can we recycle the lithium-ion batteries? I think when the first generation EV are going to retire in 2025 and 2026, we will be ready. So all the breakthroughs to enable this kind of improvement in performance and the reduction in the cost comes from fundamental material science breakthrough. So the good example to say here is, the nickel replacement on the cobalt is one of the first dramatic change in terms of reducing the cost for the lithium-ion batteries, because lithium cobalt oxide, the cobalt, is actually quite expensive. And I think early today, Dr. Jun Liu from University of Washington, Seattle has given you a very good overview of the lithium metal battery research. So I will today mention a different aspect of how to do the research on lithium metal batteries. So lithium, we all know, is extremely reactive. So in order to look at lithium under the microscope, if you use room temperature, you can actually see a very, very blur image of the lithium metal, because only with the cryogenic electron microscopy you can stabilize the electrochemically deposited lithium, because these lithium typically are surrounded by insulating solid electrolyte interface. So this is a good example to show you that in the batteries we can grow this kind of highly viscous lithium metal, and their surface is covered by SEI, like lithium carbonate, lithium fluoride, lithium oxide. So when you do the imaging, even if the top panel is room temperature, even if you do nothing, you can see the viscous is changing. And this change is not coming from the materials itself, it's actually coming from the interaction between the beam and the matter. Now with the cryogenic method, we can now stabilize the image, and you can see the beautiful lattices of the lithium metal and its SEI. So the development of the lithium metal batteries has not been a very straight pathway, because in the 1970s and early 80s, lithium metal was explored as a promising anode materials, but at that time our cathode materials do not have lithium in it. Today, with the high nickel NMC, we can afford just to have very thin lithium in the anode side, because there's a lot of lithium in the layered NMC materials. So with that, I think in the battery 500, which is the director, Dr. Liu, just gave a presentation. I just want to say that as a part of the member of the Battery 500, our main task is to characterize, understand what happened with the electrochemically deposited lithium and how we can improve its cycle life. So if you look at the cross-section imaging of the lithium, so typically when you have a lithium piece, you have to cut the cross-section. If you cut the cross-section with a gallium ion beam at room temperature, you're going to see this is a lithium foil, right? You can see a lot of very strange features, and these features are indeed coming from the gallium and the lithium interaction. So the challenge for observing lithium metal is really lithium metal reacts with everything, including the gallium. So the trick to go around it again is to turn it into cryogenic method, where you can then very nicely preserve the microstructure of lithium metal. So with this tool, we can now evaluate the different electrolyte. So you can see in the carbonate electrolyte. So this electrolyte is designed for graphite. If you use this electrolyte for lithium metal batteries, you grow this kind of highly porous lithium metal, okay? But if you change the electrolyte, you can then see the microstructure of the lithium is completely different. So when we change the electrolyte from carbonate electrolyte to ether-based electrolyte, the Coulombic efficiency increased, and many people attribute that to the improvement of the solid electrolyte interface. But in our study, we have a different hypothesis. So the hypothesis is that because of the microstructure difference, so we are using some cartoon picture to demonstrate our hypothesis. If you have this kind of highly viscous, high aspect ratio, tortuous microstructure, when you deposit the lithium, the difference may not be that big because, this is long and thin, this is short and fat. You can see the same amount of lithium. But when you discharge your battery, the lithium has to go back to the cathode. If you have this kind of morphology, remember the blue, the SEI contains lithium carbonate, lithium oxide, lithium fluoride. It's very insulating. So if you have an imperfection, then some of these lithium on this part will be totally blocked from the electrical pathway. So in the electrochemical system, even if this is metallic lithium, if they don't have access to the electron pathway, this lithium will be what we call the dead lithium. They will be electrochemically inactive. So the hypothesis is we believe that the SEI is mostly similar, but the microstructure causes a very big difference in the Coulombic efficiency for the battery. And we also studied under the Cryo-TEM to confirm the hypothesis, where in the tortuous and viscous structure, you see a lot of dead lithium, and in the large granular structure, you see very few places has the lithium trapped. And to quantify accurately the total amount of lithium trapped inside the SEI, we turned into this very simple and elegant method called titration gas chromatography. And the idea is very simple. Of all the compounds we form on the lithium metal side, they either dissolve in water or they react with water to form carbon dioxide or methane. Lithium metal will be the only one that gives hydrogen gas. So we evaluated the many different types of electrolyte, include the very bad ones and the very good ones. And once we complete to compete with me for the speech. Okay, now we're. Thank you very much. So let me continue to talk about the lithium metal anode. So when you have different electrolyte, you can see the good one and the bad ones have very different Coulombic efficiency. So according to our measurement, indeed, most of these Coulombic inefficiency comes from the lithium that's trapped, the blue part that's trapped in the SEI due to the electronic contact loss. And the different types of electrolytes has very similar. The red part is the measured SEI component. So in the low Coulombic efficiency lithium metal cells, it's mostly due to the microstructure differences in lithium metal. So if I plot the graph differently, you can see the capacity loss and the metallic lithium correlates very well. And the SEI is almost similar qualitatively in terms of its total amount. So with this work, we clarify the previous misunderstanding in the field that in the low Coulombic efficiency batteries, SEI is the major culprit. In fact, the SEI amount keeps almost identical in all test conditions, and we emphasize the importance of microstructure control for the lithium metal batteries. And as we are part of the Battery 500, I just want to say that today the lithium metal batteries made by Pacific Northwestern National Lab can actually cycle, so much better when we first started the project with very promising energy density and cycle life. So the fundamental knowledge we gained from studying the lithium metal anode really paid off. And actually, during this process, we discovered something very, very intriguing that has not previously been reported. That is when we look at the atomic resolution image of these first nucleated lithium, we actually saw a very, very disordered, almost glassy lithium. And this led to a series of very interesting theoretical studies to see why the lithium metal, the alkaline metal, has some very intriguing behaviors when we are at the very beginning of the nucleation. And that has a lot to do with the nucleation and the growth of lithium metal. So it's really at the very beginning of this fundamental study, only because in the past, lithium metal is so reactive that we don't have the right tools to study its behavior. And the glassy lithium is also one of these observations that led us to believe if we wanted to go fast charging or if we want to go to very high rate performances, we have to think about how to maintain the glassy lithium microstructures as much as possible. Right. So I hope the examples I show you highlights the importance of doing fundamental research in the discovering or optimizing the future generation batteries. In the battery technology, there are still many challenges. For instance, can we build the batteries never catch fire? Why the batteries have to replace every 10 years? Can we build batteries that last more than 30 years? Can the batteries be 100% charged? And in US, I think a lot of people are hoping the charging process for the batteries can be as short as when we're filling the gas tank of our ICE cars. So the research direction priorities, there's many directions to address the different challenges. I think, today I will just share with you some exciting results on the solid state battery. And when we say solid, it means all solid. There's no liquid inside the battery. So solid state batteries is very attractive because of its promised energy density, particularly if we solidify the layers and we can enable bipolar design. And more importantly, the safety aspect is very, very attractive. And it has a very wide operating temperature up to a few hundred degrees Celsius. So the solid-state battery research field is extremely exciting because in the liquid batteries, the interfacial phenomena is more of you have to worry about the SEI when you start electrochemically charge your battery. But in the solid-state batteries, you have to worry first the chemical compatibility between the anode and cathode and the electrolyte. So in our case, we focused a lot on the algidide LPSCl based solid electrolyte. they are actually incompatible with the NMC cathode. So we had to apply a lot of these, explore a lot of these different coatings to first chemically stabilize the battery. And then we go for the electrochemical understanding of how to stabilize both the metal anode and NMC cathode. So in this chemical review paper, we listed out all these different, we found 13 different types of interfaces, because in the solid state, solid cannot flow. So if you have any defect like a void, like a crack, actually that create a lot of actual interfaces. And because of the non-flow nature of the solid state methods, contact point is very, very important. So I do encourage people to go through this very, very thorough review on the challenges of interfacial phenomena in solid state batteries. We did have good solutions. For example, the cathode can be stabilized with simple surface coating with lithium niobates, and we can then cycle the batteries a few hundred cycles without any problems. And for the computational work my colleague did, Professor Xue Ong did, is we found also borates is a very promising coating materials. So we are able to stabilize the cathode with the LPSCl algidide-based solid electrolyte. On the negative electrode side, in the early days when people try to cycle the batteries on the high pressure, they always meet the challenge of short circuit. And if you do a CT scan of the solid state battery, you can see these tree-like dendrite features. And the trick is really when you cycle the battery. So when you make the battery, you need high contact pressure. But when you cycle the lithium metal battery, you need to release the pressure. So when the pressure goes below 5 megapascal, you can then, at a low critical current density, very well cycle the lithium solid-state batteries. So this new type of battery platforms provided us a very good opportunities to characterize the buried interface. So there's many different techniques being deployed. And to think about the batteries as all solid-state devices, you can think as, almost like in the semiconductor industry, everything is solid. There's not a drop of liquid in this battery. And the lithium ion can be shuffled between the two electrodes and producing and storing and converting large amount of energy. So it's very exciting. I think the development of the solid-state electrolyte is a very busy field. So people have sulfides, oxides, halides, new materials is still being discovered. I think just a couple years ago, the new halides was discovered, has very good solid electrolyte interface. When we have a chance to commercialize solid-state batteries, we should think about how we can build an environmentally sustainable system. We should plan it ahead, right? Don't wait until later we have a large amount of battery. We should build in the recycling ability in the system. So the solid-state batteries development is really in the early stage, probably still 10 years away, but it is indeed a very exciting research field for young folks to step in. So regarding the new electrolyte, I think lithium is not the only carriers that we can utilize. You can actually use sodium. We can find the sodium equivalent of these halides and get very nice ionic conductivity at room temperature. Right? So what we show here is you can make these solid electrolyte, the entire composition with very good room temperature conductivity, and the cell cycle pretty well. We demonstrated 1,000 cycles in the small scale, laboratory scale test cells. And this work is indeed funded by energy company Shell Corporation. So last but not least, the example I want to show everyone is to think battery differently now. So battery is not necessarily a rigid object, right? So our latest work with our partners of Qualcomm and Z-Power, we are able to produce batteries that are completely flexible, stretchable. You can fold it, you can twist it, you can stretch it, and it should still work very, very well. So this opens up a new application range where we think about IoT, wearables, and things like that. So we're very, very excited about there already a company bringing the technology for commercialization. So let me see. I think I'm at the end of my time, 30 minutes. So let me thank all the students and the postdocs who have made major contributions to the research and my collaborators and colleagues. And I want to say we're very fortunate to have the funding from U.S. Department of Energy, as well as our industry partners and the national lab partners. I'm happy to answer any questions you have. Thank you very much for listening.